Welcome back, everyone. So let's have a look at a particular implementation of Dijkstra algorithm. So we start by defining a regular connection. So this is somewhat similar to what we have defined a connection over here, for example, but this isn't a node, this is a connection. So we have a name and the associated weight. I mean, but this isn't exactly the same. In here, we are saying that this isn't a weight, but this will actually hold the accumulated cost that I need to save for each child. So you remember if during the algorithm discussion, we saw that we need to save, the accumulated cost starting from a parent until I reach my particular node. Okay, so I need to add these two numbers, which means that I need to accumulate cost as I hop on from one parent to another child. So there are two attributes. The first one is the cost, and the other one is the parent. So at least the cost will be saved, by this variable, and then the name of the particular node as well. So this is how I will define my connection. Now this, I mean, this in some sense is a static attribute, but this is a dynamic attribute, which means that I will change it while I'm traversing through my graph. Now, so how will you identify your particular connection? Okay, so that connection will be identified by a hash code, and that hash code will depend upon the name. Okay, so I'll say that if two nodes have the same name, that means that the connection object is exactly the same. Okay, so irrespective of how different the cost is, if the name is same of that connection of that node, then this means that both nodes are the same. Okay, so this is how I'm defining uh, the hash code or the identification method of a particular connection. And then I'm also overriding this equals method. That means that how would I say that two connections objects are equal? Well, I will say that those two connection objects are equal if they are mappable to this connection class, and obviously if they share the same hash code, which means that they share the same name, basically. Okay, so this is how I will define two connections being equal if they share the same name. And then I'm inheriting this node class from this connection object, and this node class has two extra attributes. The first one is basically an array of children. Okay, so I also need to save I also need to define my children in some sense. Let's say if I have a graph, let's say if I have a node, not only do I need to save, for example, what are the let's say what is the name and what is the cost, I also need to define these two child nodes or child connections in some sense. So this is an array of child connections, and then I also have to define what will be the name of the parent of this node. Okay, so this is basically this attribute. So I mean, you can you can make an argument as to why I'm defining this cost attribute in the parent and class, and this parent name object, this parent name as a as an attribute of my child class. But you can also move this attribute let's say over here, just to be consistent. But I've actually written the code by defining the cost and name as the attributes of parent, and then the children and the parent name as an attribute of the node itself. Okay, um, so now how will you compare your two nodes? Well, you'll say that, okay, if you compare them basically upon, depending upon their cost. So if the cost of one parent, if the cost associated with one node is less than the other, you'll say that return -1, otherwise return 1. Okay, and if the cost is same, then both nodes should be considered equal in some sense. Now so when will you use these methods? I'll come to that in a while. Okay, but basically whenever you have to so for example, whenever you have to see that, whether or not two connections are equal, okay. So for example, if you, let's say if you found a particular node and you want to say that, whether let's say this found node is equal to this child, current child. Obviously, this found node is a node, but this equals method is not defined for this node class, okay. This is actually defined for this connection class. So which means that, even if you compare, two nodes, the parent method will be called, okay. So this is why I've defined this equals method in my connection object, and then inherited that method or overrided that method for node as well. And when will this compatible, when it will be called, I'll just hint it whenever it is called. Now let's come on to the main function we have. So the graph is actually defined by key value item, and those key value items are, a particular node, which means that when I say a node, I mean, 4 attributes: the name of the node, the associated cost, which will be changed dynamically, its children, and its parent, okay. So the graph itself is defined by, let's say, these, the string, the name of the nodes, and, the node themselves, and a key value pair of, a hash map that contains key value pairs based upon, these two attributes. So let's define. So, then we are going to define, for example, this graph where the first node is Sibiu. So we'll say that, okay, let's define the children of Sibiu with their names and their associated cost as a connection object, and then define the node Sibiu as the node which has the name Sibiu, which has, the children such and such, which has a parent of none basically, and the cost of 0, okay. So this is how I will define, not only Sibiu. When I say a node Sibiu, I mean that, the node and the associated children of, this node Sibiu, okay. And then likewise, I define, the the node Ramnik Vulcha and Fagarash and Pitesti, and so Pitest and, Bucharest. And obviously this is circular in the sense that I'm also saying that, the node Bucharest has, let's say, two children, the one Fagaras and, the other one is Pitest. So the Bucharest has two children, Fagaras and Pitest, and likewise the Pitest has two children, Bucharest and Ramnikovulcha, okay. So Pitest has, for example, couple of children, Bucharest and, Ramnikovulcha. So this is how we'll simply have defined our graph. Then we also need to take into account, the visited, the explored set, but that explored set will only store, the string, the name of nodes basically. So because you see, I don't really care of these two attributes. The only thing that I care about is the name, and so I would not, revisit, the node Fagarash, irrespective of whether or not, the name that exists in my visiting list shares these two attributes, which can be different, okay. So I don't really care of, the other attributes, as long as the name is the same. I don't want to revisit, my that node, okay, irrespective of the actual attributes or the parent or the other attributes of associated with that node. So that is why this explore set is a hash set of strings, not the hash set of nodes, okay. But the queue, or let's say the priority queue that I need to maintain, is a priority queue of nodes, because you see, I need to, well, whenever I'm exploring, I need to explore that node first which has the lowest cost, okay. So I need to actually save the node itself, just to see, how will how I need to explore that node first which has the lowest cost, and that is where this comparator will come into play, okay. So this comparator will tell me that, which node has the lowest cost, and therefore it will explore, or let's say it will queue, or it will query that node first. It will pop that node first which has the lowest cost, okay. Right. So this is why I have defined a priority queue based upon this customized comparator. So then everything is else this is the same. I define my source node, I define my goal node, which are the actual node objects, and then I simply add, my source node, the string name of the source node into my visited list, and I add the source node itself to my queue, and then start exploring, my queue until it is empty. Obviously, this queue dot poll will give me, whatever the lowest element in terms of comparison is, with respect to my node, and then I'll simply I'll simply print the node, and then this is the goal check. So you remember that, while we are visiting a parent, while we are exploring a parent, before exploring its children, we need to check that whether or not this is a goal node or not. If it is a goal node, then, well, then what? Then we simply get the path to that goal node. And by that, I mean that, for example, if you encounter, let's say, Bucharest as your goal node, then what you need to do is basically go to the parent of Bucharest, and then go to its parent, and then go to its parent until you reach your source node. So this is the hopping strategy that we follow over here. So we have defined a separate function for that, which basically does the same. Until my current parent is not null, I basically get to the parent of my current parent, and then, to its parent, and to its parent, and so on and so forth, until, and then while I'm hopping that, I also add it to my, let's say, collections. And then obviously, if I start from the goal node and I add, my parent node into the list, I need to reverse the list, because I need the path from source to goal, not from goal to my source. Okay, this is why I'm reversing it. So this is what happens, when you reach your goal node. Okay, so this is what happens when you reach your goal node. Okay, so this, we call this function, and then we check that if the graph has information of this current parent, then what we'll do, well, then we'll simply check that, we'll simply explore, the children, and for each child, what we'll simply do is, well, we'll check that whether or not this child exists in explore or frontier. If not, then we'll simply insert it in frontier, okay, or the queue. So here we are simply checking that whether or not this child exists in my visiting, in my explore set, or in my queue set. If it doesn't, then, I will actually create a node with the current child name, and obviously I'll update the parent and the cost of this child. Okay, so whenever we are doing insertion, we are saying that, okay, update the parent of the child and also update the cost. So this, the accumulated cost is basically, so the accumulated cost is basically whatever the cost of the current child is, and whatever the cost of reaching the current parent is. Okay, so we'll simply update these two attributes, and add this node to my queue. And then, there's this second statement, else if, if the child is already present in frontier with a higher cost, then replace the child at frontier with your then replace the node at the frontier with your current child. Okay, so this is what happens in here. So I'm checking that whether or not, if current child exists in this queue, then check if it has a higher cost, then, replace that that node in the in the frontier with your current child, and then, break it. So this is how the algorithm works. It's an exact, similar representation of this algorithm that we have already studied. If you run it, why does it say this is strange. So now it runs. Okay, in any case, so this will give you, the path, the goal node, which is, the path. I know that, the path of reaching Sibiu to Bucharest is, via Râmnicu and Pitești, and so therefore it will give you this path, but it will also give you, the node that that are explored. Okay, so I'm also printing whatever, you know, whatever the order of the exploration is in this case. So obviously first Sibiu, then Rimnikovulcha, Fagaras, Pitest, and Bucharest. Okay, so this is how, remember, this is how, you know, the this is how we actually query our nodes from this frontier. Okay, so this was the particular implementation of Dijkstra algorithm in Java.